Hi, in this video, we want to take a look at getting into keras with R. All right, so keras is part of TensorFlow. It is part of machine learning. This is some good stuff. This is some exciting stuff. And we're going to do a quick start. We're going to dive in head first into this, and we're going to be working with the code to start generating a model like that, hitting the ground running. Now, this code, this example is modified from tensorflow.rstudio.com. Now, why should you use TensorFlow with R instead of Python? All right, so to me, the main reason why you would choose R over Python for this project is just accessibility. I find that it's much easier to get keras and TensorFlow going on R than it is on Python. R, all you got to do is you go into the package that, go to the package website. It gives you like a GitHub package to download. You run one function, you wait a bit, boom, you're up and running. The biggest advantage I find with R over Python in a lot of situations is that getting the stuff that you want is so quick and easy. A lot of the tutorials on getting TensorFlow into Python involved uninstalling Python and then reinstalling Python. If I have to go through all that trouble and I'm under pressure to produce, it makes it so it's not a feasible solution. Also, if I have things about my current setup of Python that I don't want to change, uninstalling and reinstalling wipes all that out. So I feel like this is a major advantage of R. R is a lot more accessible on this front. All right, so now let's dive into the example and start digging in. Oh, and also the code to get TensorFlow installed for R is on this website. You can click on it and you'll be able to work through it. It's the fastest way you can find. All right, so if you watch my videos, you know that I try to not load packages. I avoid it as much as possible because I don't want to have confusion between different functions. So in this example, I'm going to be using double colon notation for the keras package every single time. And I'm able to do that. In this code, in the example from RStudio, we're going to be using the piping operator from the McGritter package. So here I went ahead and just loaded that. All right, I'm going to suppress some of the digits so that we won't get blasted in the face by numbers. And something that is interesting about the keras package, so here I'm invoking that double colon notation, is that for their data sets, it's called as a function itself. To get the actual data I want, I use a function instead of using the data function, which is a standard way in R. It works out all the same. We don't really care. We just have to know the difference. Now, this data set is images of people's handwriting on digits. This is the MNIST data set is like baby's first deep modeling problem. All right, so what we want to do, we want to take images of people's handwriting of digits 0 through 9, and we want to correctly classify the image as the number that they intended to write. Okay, now in this data set, there are images, and in particular, it's a 28 by 28 grid, and we have, for our data, we have representation of how light, how dark each of the individual points are on that 28 by 28 grid. Okay, so this ends up being an array instead of a data frame. Okay, so I've got a whole bunch of images, I think it's 70,000 about, and then 28 by 28. So it's a 70,000 by 28 by 28 array. Okay, so each of my data points corresponds to an image. So each of my data points is a 28 by 28 representation of a picture. Okay, so what I'm going to do is I don't like to have people give me the training and test set. I like to be able to just work with the entire data set, and I want to split things the way I do. I do it. I'm particular that way. And so to take the training data and the test data that the keras package gives me by default, I'm gonna bind them together using a bind, an array bind from the array bind package. Okay, and here I'm just doing it along the first dimension. Remember, it's a 3-dimensional data set. Okay, and I'm doing effectively the same thing, but here for the target variable, they're vectors, so I just use the concatenate function, which is C and R. All right, so now I've got my data. I've got X, which is a 3-dimensional array. I've got Y, which is a vector of the same length as the first dimension of X. All right, so now in my X data set, all the values are from 0 to 255. You know, it's 2 to the power 8 minus 1. Okay, so this 0 to 255 represents how dark or light the individual position in the grid is. All right, now something that does not get talked about enough when we're doing deep learning, a lot of deep learning algorithms like things to be on the 0 to 1 interval. Okay, so I have everything from 0 to 255. To get this onto 0 to 1, I just divide everything by 255. And so what I'm going to do is I just divide X by 255, and boom, it puts everything from 0 to 1 for me. All right. All right, so now that I've got my data like prepped, I'm ready to go. So something that's nice about this is there isn't much data prep for this problem. In real problems, data prep is king. Make sure you do your data prep. Okay, so let's go ahead and go through. I'm going to define my keras model. Now, something to realize is I don't actually use data on this step. All right, so we're going to go with a sequential model. Now, the layer flatten, what that does, that takes a 28 by 28 grid and converts that to one long row of data. So what's going to happen is each 28 by 28 grid gets converted into a row vector. Next one gets converted into a row vector, row vector, row vector, and then they get stacked on top of each other so that now, after I pass the data in, when I'm going through to fit my model, I actually have a data frame. So in almost all situations, in some way, some shape, some form, my data is being represented by a data frame. So always keep that in your mind as you're working through your problems, that even though what you're looking at looks different, probably for you to be successful, you probably have to shape it into a data frame, whether we like it or not. Now, layer dense, what we're going to do is we're going to have a whole bunch of nodes that we have inside our neural network. Right here, and the author of the example picked 128, and the activation function is ReLU. All right, so ReLU is fast, then it's angled. So it's a piecewise defined constant, then linear function, or linear function, then constant. And the constant will be a 0 most of the time. I believe in this example, it's always 0. Now, something that's nice about this is a very simple, algebraically simple function, but it's very powerful and it's very flexible because of that bend in the piecewise aspect. That piecewise defined aspect is where we get a lot of that oomph for machine learning. Now, something that we'll do is we'll go ahead and we'll get rid of certain parts of my neural network, certain connections, because we'll have a lot of them in there. And by getting rid of things, I can protect myself from overfitting. Remember, the more parameters I have, the more likely I am to overfit. Okay, so this dropout is working to get rid of some of those parameters so that way I'm less likely to overfit. Now, the next dense layer, we have 10 units going on. Now, remember that for our target variables, it's the digits 0 through 9. I have 10 of them. So the reason why that we have a 10 here is because I have 10 distinct target variable levels. All right, so I have Now, as like, think of it as a character, as categorical data, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the levels of my categorical target variable. Now, to specify that I'm working in the categorical sense, activation equals soft max. And now for the compile, so this is saying I want to measure by accuracy. I want to optimize with atom. And my loss function is the sparse categorical cross entropy. Okay, so remember, entropy is a big heavy hitter whenever I'm working in categorical model fitting. Okay, so now, as I did this, you'll notice that I did not put any data in. What I did was I specified what is the structure of the model. That's all I've done. I haven't actually fitted the model at all. The actual data itself has not been included. So now we can see that if I use a summary function on the model structure, we can see that we have layer, then output and shape, and number of parameters. So here the first layer flattens, so it takes that 28 by 28 and converts it into a row vector. And so here we can see 28 squared. We have 0 parameters. We're not fitting anything. We're reshaping the data. Dense 1, here we have 28 nodes there. And this is the number of parameters. So this is the number of connections between the columns of my data and going. So from here, this layer, each column going to each node, including a bias term, goes there. Now, when we talk about deep learning, bias corresponds to the intercept or the constant, and weights correspond to coefficients in college algebra. Now here we've got dropouts, and here we have potentially 128 that we could be dropping. And then here we have 10 more nodes, and then we have 128 plus 1 times 10 gives me 1290. All right, so the plus 1 to give me 129, that is for the bias term. That is for what would be the constant, the y-intercept in college algebra. So here is our total number of parameters. Now, if you add up our number of parameters, which is just this number here, and then we look at how many observations we actually have, we notice that we have more parameters than we have of observations. This is a very dangerous situation in terms of model fitting. I am very prone to overfit on this model. Now, a lot of people have worked with the MNIST dataset. A lot of people have tinkered with it, have played with it, and they discovered that this particular model structure works very well. I strongly recommend that you make sure you have more data than you have of parameters in your real life situation. Otherwise, you are taking a severe risk at overfitting. Now, in the more data points I have per parameter, the safer I will be from overfitting. It works out here that the model structure and the data match up very, very well. And so since there's a nice correspondence between the problem at hand, the data, and the model structure, it's okay, and we ended up not getting smacked in the face for overfitting. But in real life regular problems, this is a very dangerous ratio. All right, so now let's go ahead and let's fit our model to our data. Okay, so I'm going to take my model structure and I'm going to pass it to the fit function in keras. I'm going to specify my training data, and this is validation also, training validation, my target values, so number of epochs, and I like to do a 50-50 validation split. That's just my preference. Other people prefer 70-30. I like 50-50. And verbose, this is how much information I want printed back to me so I will know what's going on. And then I want to plot to see what's going on. All right, so when I plot, what's going to happen is it's going to take this loss function, my entropy, and it's going to take my accuracy and give me feedback on what's going on. All right, so here we can see as it goes along, so here at 4, training loss is going down, going down, going down, and then accuracy is going up, up, up on the training. And in validation, we have a similar pattern, but not as steep. We can see that we get a little bit of improvement and then it flattens out. We get some improvement, then it flattens out on the validation. So the validation definitely is the more informative one, the one that I'm more interested in looking at. Now, remember, if I see my training and my validation statistics split and start getting far apart, that's a sign to me that I'm overfitting and I'm running a risk. Okay, so here, this is not much of a vertical difference between the two. This is pretty small. So I'm not too worried about overfitting. But if I was to continue going further and further and further, we can see that the accuracy on the training might reach 100%, while the validation probably is going to stay stagnant. All right, so now let's go ahead and get the actual model values for our data set. So what we're going to do, I'm going to take my model, I'm going to take my training validation data, and I'm going to run the predict function. Okay, now remember that it's trying to model which digit am I looking at, 0 through 9. So I go ahead and I put 0 through 9 as the call names. The default for this predict function does not specify what the predicted value is in the column names. And so that makes it a little bit harder to interpret what's going on. I go ahead and put the column names on there. And let's go ahead and just take a look at the first few. All right, so I can see here in the very first row that for all practical purposes, it's saying its model probability of it being a 5 is 100%. And then the model probability of it being a 0 is a 1. The model probability for it being a 4 for row 3 is 1. And we can go down and look, and we can notice that it's not exactly perfect, but it's doing a pretty darn good job. All right, so now I want to get a feel for how accurate is this? Are there any shortcomings? Are there any problems? Is there anything I need to know about? All right, so what I decided to do, I wanted to plot a histogram for each modeled digit and each correct digit. And I want to look at the histogram to get an idea of any shortcomings or any strengths of this particular model. All right, so what I'm going to do, I'm going to take my predicted values, I'm going to pass it to ggplot. ggplot wants a very specific format. It wants a long format, tidy format. All right, so what I'm going to do, I'm going to make a data frame with my predicted values. I'm going to say that the correct digit column is my target value, and the data frame function doesn't like having numbers as the leading in the names of the data frame for the columns. So here, what I'm going to do, I'm just saying check names equals false. Just don't mess with the names. By default, what this would do, this would put a capital X in front of 0, 1, 2, and 3. I would have like a capital X9, capital X8, capital X7, and so on. And so it just kind of messes things up. It's not a problem for this, so I just leave it alone. And then I'm using the gather function from tidyr. Got model digit, model probability. And now let's go ahead and plot it. All right, there's a lot to look at here. What's going on is that, let's look at this little corner right here. This is a histogram of the modeled probabilities of the digit being a 0 when in fact it truly was a 9. So no, correct. The correct value is a row. So here, the correct value is a 0. Here is the modeled histogram of the model probability of a 9. here the digit is a 1. Here's the modeled probability of being a 9. The correct digit is a 2. This is the modeled probability of it being a 9, and so on. So the diagonal are the modeled probabilities of the correct, and the red are the modeled probabilities of it being incorrect. Okay, so overall, this is really good. This looks really solid. Now, if I look through, though, I can see that if I go along 7, I can see that there were some values kind of sticking out here. So here, the correct digit is 7. We can see that there are times that it had a strong modeled probability of it being a 9. For 7, we can see that there are times that there's a strong modeled probability of it being a 4, of being a 2, of being a 1. All right, now, if you think about the number 7 and think about ways that you can make a 9 look like a 7, yeah, this makes sense. But so here, with what I've built this time, and I did this a couple of different times before I made the video. Another iteration, the problem was with 3, but here on this iteration, it's only 7. So going forward, if I want to improve the model, knowing that 7 is the problematic digit gives me a direction to work in, a direction to try and improve on. All right, well, that's all I've got for you. Take care and goodbye.